Welcome to a lesson on how to determine matrix exponentials for the general case where we have an n by n matrix with n linearly independent eigenvectors. In the previous lesson, we found matrix exponentials for simple cases, such as for a diagonal matrix and a 2 by 2 matrix A, such that A equals lambda I plus B, where B squared equals 0. Now we look at the general case to determine a matrix exponential. To begin, we need the following interesting result about matrix exponentials. For two square matrices A and B with B invertible, we have e to the power of BA B inverse equals B e to the A B inverse. This can be seen by writing down the Taylor series first. Let's begin with the square of BA B inverse. This is equal to 2 factors of BA B inverse. Notice in the middle here we have B inverse times B, which is equal to the identity matrix. And then A times I times A is equal to A squared, giving us BA squared B inverse. And by the same reasoning, the k power of BA B inverse equals B a to the k B inverse. Now we write down the Taylor series for e to the power of BA B inverse using the definition below. E to the power of BA B inverse equals I plus 1 factor of BA B inverse plus 1/2 times the square of BA B inverse plus 1/6 times the cube of BA B inverse, and so on. From here we replace I with B times B inverse. Notice all the terms have a factor of B as well as a factor of B inverse. For the next step, we factor out B on the left and B inverse on the right. Notice in the middle here, we're left with e to the power of A. So now we have e to the power of BA B inverse equals B e to the A B inverse. Now that we've proven this, we'll come back to this later. Now, given a square matrix A, we can usually write A equals E D E inverse, where D is a diagonal matrix and E is an invertible matrix. This procedure is called diagonalization. If we can do that, the computation of the exponential becomes straightforward, as e to the d is just taking the exponential of the entries on the diagonal. And if we include a factor of t, we can compute the exponential. We have e to the power of ta equals e times e to the td times e inverse. Now it's important to remember, to diagonalize matrix A, we need n linearly independent eigenvectors of A. Otherwise, this method of computing the exponential does not work. From here, we let lambda 1 through lambda n be the eigenvalues of matrix A, and the vectors v1 through vn be the corresponding eigenvectors. Then we form matrix E using the eigenvectors as the columns, and we also make a diagonal matrix D with the eigenvalues on the diagonal as shown here. And now we compute A times E. So on the right we have A times E. Multiplying by A we have the next line. And then we replace A times V1 with lambda 1 times V1. We replace A times V2 with lambda 2 times V2, all the way out to replacing A times the eigenvector Vn with lambda n times Vn. Next we factor out the eigenvalues on the right, which gives us matrix D. And notice on the left we have matrix E. So now we have A times E equals E times D. Since the columns of E are linearly independent, as they are linearly independent eigenvectors of A, we know A is invertible, and since A times E equals E times D, we multiply on the right by E inverse, simplifying, which gives us A equals E D E inverse. From here, if we exponentiate both sides of the equation with the base of E, we have E to the A equals E to the E D E inverse. Here's where we use the property that we proved at the beginning. E to the power of E D inverse is equal to E times E to the D times E inverse, which gives us E to the A equals E times E to the D times E inverse. Multiplying the matrix by T, we have the formula we use to determine E to the power of TA. Again, E to the power of TA is equal to E times E to the power of TD, which is the matrix shown here on the right, times E inverse. This formula gives the formula for computing a fundamental matrix solution e to the ta for the system x prime equals a times x, in the case where we have n linearly independent eigenvectors. This computation still works when the eigenvalues and eigenvectors are complex, though then we have to compute with complex numbers. We won't deal with that case now. Let's look at an example. We're asked to compute a fundamental matrix solution using the matrix exponential for the system. Then compute the particular solution for the initial conditions x of 0 equals 4 and y of 0 equals 2. Let's set this up on the next slide. We let A be the coefficient matrix with entries 1, 2, 2, 1, and we first compute the eigenvalues, which are 3 and -1, and the corresponding eigenvectors are 1, 1, and 1, -1. You may want to pause the video and verify this. The next step is to set up A equals E, D, E inverse. So again, we have the given matrix A equals matrix E is the matrix formed using the eigenvectors as the columns. So we have the eigenvector V1 and the eigenvector V2. And then we have times matrix D, where matrix D is the diagonal matrix where we have the eigenvalues along the main diagonal. And then we have times E inverse. Now that we have this, we know the matrix exponential e to the power of TA is equal to E times e to the power of TD times E inverse. So again, the first matrix is matrix E, and then e to the power of TD is the matrix with entries e to the power of 3t, 0, 0, and e to the negative t, and then we have times E inverse. The next step is to determine E inverse, which is shown below. E inverse is equal to -1/2 times the 2 by 2 matrix with entries -1, -1, -1, 1. So for the next step, we pull the -1/2 to the front, and then multiply the first two 2 by 2 matrices, which results in the 2 by 2 matrix with entries e to the 3t, e to the negative t, e to the 3t, and negative e to the negative t. Now we multiply by the next matrix, and then perform scalar multiplication to get the matrix exponential shown here on the far right. From here, if we were looking for just a general solution, we would have the vector function xy equals e to the power of ta times the constant vector c, which is shown here on the right. But again, we're looking for a particular solution because we are given the initial conditions x of 0 equals 4 and y of 0 equals 2. So if we did use a general solution and substituted 0 for t, notice how we would get c sub 1 equals 4 and c sub 2 equals 2, which actually is the original vector b given by the initial conditions. And therefore, it's much easier just to use the property that e to the power of 0a equals the identity matrix, and we find the particular solution is just e to the power of ta times the vector b, which is the vector 4, 2, given by the initial conditions. So we have our particular solution is the vector function xy equals, again, the matrix exponential times the constant vector 4, 2, which if we multiply out and simplify is shown here on the right, where x equals 3 e to the 3t plus e to the negative t, and y equals 3 e to the 3t minus e to the negative t. I hope you found this helpful.